Hello everyone. Today we are going to uh, work on another example, kind of extension of the complex Fourier transforms in multiple spatial dimensions. And this will be the last lecture on the complex Fourier transforms and the analytics part of the course. Okay. So the multiple spatial dimension is like, so far we have only investigated, if you remember, 1D problems, 1D examples, one dimensional in X. And the question now becomes, what if we have like multiple spatial dimensions, like we have a two-dimensional space or three-dimensional space. So the general method or approach that we are going to take for this is that we are going to remove each spatial dimension x, y, z separately using appropriate integral transforms. So in any dimension, for example x, y, z, we will treat them separately and take the proper or appropriate integral transform in that dimension, and then solve the PDE, the resulting PDE, which is going to be much simpler, right? Because for example, Fourier transform is going to convert the derivatives into multiplications. Okay. So let me give you an example, so this would be clearer for you. So let's write an example. Consider an instantaneous slug release as a point source in a steady state uniform flow field moving in the x direction. Find the concentration of that tracer as a function of space and time. Okay, so this is the question. We release the slug in a steady state uniform flow field that moves in the x direction, and we want to find the concentration of that tracer as a function of space and time. Okay. So the governing equation of this tracer motion is as follows. So it is partial c over partial t plus the advection term in the x direction, which is going to be v partial c over partial x, and v is the speed of the fluid, minus the diffusion term in the x direction, dx partial square c over partial x square, minus the diffusion term in the y direction, which is going to be dy partial square c over partial y square, minus the diffusion term in the z direction, which is going to be dz partial square c over partial square z, equals to, so this equals to the source term, which is the release of the slug point, which is the release of the slug as a point source. So it's gonna be, I'm gonna write it down here, equals to the source term, which is m delta function of x minus x0, means it is released at x0, delta y minus y0, released at y0 and z0 at time t0. So this is going to be our source term, which is g x y z t in the general formula that we had. So the initial conditions are x0, y0, z0 is the initial location of the point source. The solution is between x minus infinity and plus infinity. It's also between y between minus infinity and plus infinity, and z is also between minus infinity and plus infinity, and t is greater than 0. The boundary condition c and the gradient of c goes to 0 as x, y, z, all of them approach plus or minus infinity, and the initial condition is c, x, y, z, and t at time 0 is 0. So we don't have any concentration at time 0, and it's only we release a source point at a particular time times t0 and x0, y0, and z0. Okay, so this is the problem statement, and now you have this in 3D space. X, as you see, we have it in x, y, z plane, and now we want to solve this and see what would be the solution here. Okay, so let's get started. We first remove, the advection term like before by changing to a characteristic coordinate. So this is not necessarily required, but I mean, this is gonna simplify our equations, and we can just use the formulas we knew before, and it's gonna give us a nicer solution. Okay, but you don't need to do that, and you can still keep that and solve the equations. Okay, so I'm gonna define a characteristic coordinate based on these eta, which is defined as x minus vt, and then I just change the variables here based on this new characteristic coordinate. It's similar to the previous problem, and because now we are this means that we are now in the reference frame of the fluid, like we are moving with the fluid, which is moving with speed v in the x direction. So thus we don't see any advection, so this is going to be 0, and we only see the diffusion if you move with that reference frame. Okay, So if you change that equation with this new variable, we are going to get partial c over partial t minus, so the advection term is removed. We are going to write dx partial square c over partial eta square minus dy partial square c over partial y square minus dz. So dz and dy, those diffusion terms do not change here. So this equals to g eta y z t, right? So this is when we change our coordinate system to a characteristic coordinate system. So this is, I'm going to write it as equation 1. And the boundary conditions, grad c goes to 0 as eta y and z goes to plus and minus infinity. Okay, so now this is the first step. The second step is I'm gonna apply and take a complex Fourier transforms of this equation in the eta direction. Okay, so the first is complex Fourier transform in eta. Okay, so I'm gonna get so the Fourier transform of C in eta is gonna be beta eta. I'm gonna show it with eta, beta eta y z t equals to the integral transform from minus infinity to infinity, the integral of I e to the I beta eta eta c eta y z t d eta, right? So you can just look at the definition of complex Fourier transform, and this is how we are going to transform the equation. So now I'm just going to write this is the definition. I'm just going to transform equation 1. So Fourier transform of equation 1 is going to be partial c hat. C hat means the c in the beta eta space. Okay, partial t minus, so the second term, this term, as you may remember, the differentiation is going to become converted to multiplication in the beta eta space. Okay, in the beta space. So if you use a formula we derived before, it's going to be minus I beta eta to power 2, because this is second derivative dx times c hat and then the other terms are not gonna be different, like, because the derivatives can come out of the integral. So it's gonna be partial c hat over partial y square minus dz partial square c hat over partial z square equals to g hat. Okay, and this one, if you calculate that, minus I square is going to be minus 1 times minus 1 is just going to be beta eta square plus beta eta square. Okay, So this is the first step. In the second step of this equation, we still have this equation, right? So this is going to be our second equation. So now, in the next step, I apply a complex Fourier transform in y direction because I want to also simplify this term. I want to convert this to a multiplication to be able to solve this equation. This equation is still hard to solve, right? It is a PDE, partial differential equation, and I want to convert that to an ordinary differential equation, okay? So a complex Fourier transform in y direction is the next step that we are going to do. So here we are going to have C double hat beta eta, and then second we have beta y because we are going to go to the beta space in the y direction. Z t equals to integral from minus infinity to infinity to e to the I beta y c hat, now c hat, which is this one, right? So we just put this function here, beta eta y z t dy. Okay, so this is the complex Fourier transform of c hat into in the beta in the y space. Okay, so it's gonna be in the beta y space here. So apply this Fourier transform to equation 2. So if we apply that, we are going to get this. We're going to get partial C double hat over partial t plus beta eta square. So it's a constant, it's going to come out. Beta eta square dx C double hat. And then the second term is going to be similar to this one. So I'm going to have plus b beta y square dy C double hat. And the third term, we're going to still have that, right? Because this is not a function of y. So it's going to be dz partial square C double hat over partial z square equals to g double hat. And this is equation 3. Okay. So you see now the equation has become simpler to solve. We only have one high order derivative. So as you may imagine, the third step is to do the complex Fourier transform in the z direction to get rid of this term. So step 3. Complex Fourier transform in z direction. So if we apply that, we are going to get C triple hat of beta eta beta y beta z t equals to The integral from minus infinity to infinity to e to the power I beta z z c double hat, so this is this function, of beta eta beta y z t dz. So this is going to be the definition of the third complex Fourier transform in the z direction. And then we are going to apply this to equation 3, to this equation. So let's do that, and if we do that, we are going to get partial c triple hat over partial t plus beta eta square dx c triple hat plus, again, these beta y square dy is going to come out because it's not a function of z times c triple hat. And now we have the third term is also going to be converted into a multiplication. So we are going to have b beta z square dz c triple hat equals to g triple hat. And this is our equation 4. And now the initial condition here is c triple hat at t equals to 0 is 0. Okay. So as you see, with these three complex Fourier transforms that we did in each space, so this one in eta, this one in each dimension in y direction, and this one in the z direction. So these three, we were able to convert this partial differential equation, which is kind of hard to solve, into this ordinary differential equation in the beta space, like different betas, right? So this equation is very simple to solve. We only have one time derivative here, and we can simply solve this equation. So it has a general solution and a general solution. And based on this source term, we can solve that. Okay.